Welcome to our IROS presentation. Today we will present a way for closed-loop robotic cooking. We will do it on example dish of scrambled eggs, and for a feedback we will use a salinity-based taste sensor. Starting with motivations for this paper, we look at the currently available solutions on commercial market or entering commercial market. Looking from the left, we have a Samsung chef, which is two robotic arms which do pre-programmed move in a very structured environment, and they ask a human to help them with cutting ingredients, so they need a lot of oversight, but they give user some opportunity to change a recipe if it's desired. Moving to the picture in the middle, it is a solution made by Spice, which is a company which is actually running two restaurants. The restaurants are in the USA, and they have this setup of rotating woks there. So if you think about variability of this robot and how many dishes it can do, it is limited to what you put in, and it's limited of course to one pot dishes, so it doesn't really have a way of being scaled to some general purpose cook. And moving on the right, we have Molly Kitchen. It's a solution which is commercially available and can be bought. It uses two robotic arms which do pre-programmed moves, and it has many recipes pre-programmed, although it still depends on the human as comes to cutting and preparing ingredients and to putting a correct amounts of these ingredients in the boxes all around this setup. And as you see, those robots do not use a lot of feedback as a human would do, which we use a taste, smell, we look, and we touch, we feel temperature, etc. Therefore, we would like to move somewhat closer to a human as comes to cooking. And human is very skilled about assessment of a food, and it uses feedback from many senses. And even if some of those senses are turned off, like we see here, it can still tell awful lot about ingredients used for the dish, as we are shown in this MasterChef contest here. The problem we will be tackling here is cooking scrambled eggs, and as you see here, we start with some eggs, and idea is that we mix them, but how much mixing we need for a proper scrambled eggs? Does it matter when we do this mixing? Probably if we did mixing only before cooking, it would need a lot of mixing, but if we do during cooking, a little bit less. How much mixing is enough? How we sense something like amount of mixing? There may be some actual perception needed to measure it, as it's not a simple sensor output. And our hypothesis is that we will use a robot with conductivity sensor, which can do a lot of measurements. Imagine 70 measurements of the eggs, and we will just compute a mean and variance of those measurements. Mean telling you how much salt was used, and the variance will tell you how well the eggs are mixed. And the variance will work for it, as the white and the yolk have different conductivity. So if yolk is mixed with white for more and more measurements in more and more points, then the variance will be falling, and we will have a good measure of mixedness. So we say, if human cooks eggs and we run those measurements on those eggs, We can then use a robot to cook eggs, and then on those eggs do the same measurement, therefore adjust cooking of those eggs, and we have a control loop where those measurements can be used to adjust how we are cooking. And after a few iterations we should have eggs which are very similar to those cooked by a human. And that is because we minimize error between human and cooked eggs. Human cooked eggs and robot cooked eggs. Moving to methods. To run this experiment we use UR5R, which is fitted with a mixing spoon, and it is fitted with salinity sensor on the top. The salinity sensor is effectively measuring conductivity, which is a good measure of salinity given that temperature is constant. The robot is using induction hob for cooking. Eggs in pan are provided by a human, and the salt meal is also provided. And the salt meal is an easy way for the robot to add a prescribed amount of salt to a dish. And moving to the right part of the screen, we have a meal pressing time on the x-axis and mean conductivity on the y-axis. As we see, we have a fairly linear function, so we know we have a linear relationship between how long the meal is pressed to how much salt is added to how the mean conductivity is changing. And analyzing this plot a little bit deeper, our conductivity starts just below 6, which is for 0 time of pressing meal, which is a natural conductivity of the eggs plus some residual salt added there if you just tap on the meal, but the eggs itself has around 5. And then as we are pressing the meal longer and longer, we have a linear relationship. Usually human would like around conductivity of 10 millisiemens, which is around here, but it goes much farther as comes to our possibility to measure. Now moving to modeling of how mixing is affecting our variance and how it is affecting our mean conductivity. So starting from the left, we have run a different amount of mixes and performed a measurement on it. So if you look at the variance of the salinity, we see it falling in exponential fashion. So we have fitted a curve as shown on the plot, which has parameters shown in the legend. And we also did the same for the mean, which is shown on the bottom left. So we can conclude that adding additional mixes is not changing the mean conductivity, and therefore only how long we press the salt is changing it. We of course have a lot of error here, but well, we are sensing it in the random points, so it will always be some error there, and the error seems to be the highest at the beginning, and that's where this random error is the highest, as you are sensing always only the white or only the yolk. So a few random measurements can change a lot here. Moving to the right, we have a plot of how the whole experiment is run. So we start with someone cooking eggs. Usually you would cook, you would set it for how you like, or for some experimental reasons, like you could set it for a medium mixing and medium salt or some other condition. Then the robot would do some testing around 70 measurements as we spoke before, and we will have a desired value for the mean and for the variance. We will pass them to a controller, which will use them as a goal values, and the controller will tell the robot to cook some eggs with initial conditions. And those initial conditions are applied, eggs are cooked, and the salinity tests are performed. We have our goal, we have our measurements, so we can compute error, and it's sent back to a controller which can set new mixing time and new salt adding time, and after a couple of iterations we have our scrambled eggs. Moving to results, we have 3 dishes here which are measured. None of them have any salt added, so we have only kind of an influence of how much you mix and how much you scrambled and how long you are frying it. So starting from the left, we see kind of an extreme. Those are very highly fried scrambled eggs, so you see a lot of air gaps there, which are lowering salinity mean. So that's one of the boundaries of it. If you are actually doing some dish like it, which you probably don't want to do, it will influence measurements. But salinity is of course very high here, as you always measure either white or yolk here. There is not much mixing done. Then in the middle we have much more mixing there, so we have some reasonable mean there now, and variance fell down. And on the right we have also some reasonable mean, because mixing is of course there is some noise, but it's not changing the mean too much, and the variance is falling down. And then running it on actual dishes made by a human, we see that the resulting eggs are going towards the presented eggs quite quick, usually 2 iterations. And if we look at the plots over there, we see we are always starting with very high errors, but usually after 2 iterations they are very low. Therefore the produced eggs are very similar to those provided by human. Moving to discussions, this setup has some obvious problems. First of all, it needs electrodes to be stick into a product. So if it's something solid, it makes it much harder. There's clogging issue, so the eggs may get attached to electrode, which of course needs some human oversight to clean it. So it's not very practical. The temperature dependence I was talking about is a problem. Measuring is quite slow, as we need a lot of measurements, and it could be improved. Also, manipulations of the system is quite limited, and to make it practical we will probably need more of it. And also perception is hard-coded, so there is a huge area to apply machine learning to either build its own metrics there, or model the effects of action there, even take actions to store experience. That's a huge area which can be improved. Thank you for attention, and have a great conference.